Yes. Hello friends, welcome to the session. See the continuation of chapter 4, that is inverters concept. In the last session I discussed about what exactly definition of inverter, what the main motivation of developing the inverters, and what are the different types of inverters we are using. And the basic concept that I discussed, what is differences between voltage source inverter and current source inverter. Okay. Now we'll start with in detail about single phase bridge inverter. Okay. In this session we'll continue with bridge inverters. Under that, first one is single phase bridge inverters. Yes. Start. Note down this. Single phase bridge inverters. Single phase bridge inverters. Yes. The single phase bridge inverters. This in single phase bridge inverters, based on configuration, these are classified into two types. Yes. One is single phase half bridge inverter, half bridge inverter, single phase half bridge inverter, that is HBI. Then single phase full bridge inverter. Yes, single phase full bridge inverter. That is FBI. These are based on configuration we are using. Okay. First we'll start with the single phase half bridge inverter. But there is some drawbacks are there in half bridge inverter. That's why we are implementing full bridge inverter. Okay. Study of single phase bridge inverters are nothing but a study of half bridge and full bridge inverter in detail. Okay. First go through with the single phase half bridge inverter. Half bridge inverter. Single phase half bridge inverter. Okay. First I will draw the configuration. Later on we will see what is waveforms, what is the operation, what is waveforms, and what is the analysis that I want to discuss. Yes. Listen please. Now this is the configuration of half bridge inverter. This is Vs by 2. Yes. Vs by 2. This also Vs by 2. I am drawing a half bridge inverter. That this is one switch. This also switch arrangement. Here we are connecting load. Yes. Input is source, voltage source. Then input is voltage source means it is a voltage source inverter. But every time no need to tell voltage source inverter like that. If the input is voltage source, that is a voltage source inverter. That is, it is a single phase half bridge voltage source inverter. If the input is current source, then it is a current source inverter. But here we are using voltage source now, that's why voltage. That's why no need to write again voltage source inverter. Okay. If it is inverter means you take voltage source inverter. If it is mentioned that current source inverter means you take the current source inverter. Like that you follow. Okay. Let this is S1, S2. I told already. In voltage source inverter means we are also using feedback diodes. Voltage source inverter requires the feedback diodes. Yes, this is D1 and this is D2. Okay, let this I0 is the load current, V0 is the load voltage. Yes, this is the configuration of single phase half bridge inverter. That is, the single phase half bridge inverter consists of how many switches? 2 switches plus 2 diodes. It is a combination of 2 switches plus 2 diodes. These are the main switches. Main switches. Then what about these 2 diodes? These 2 diodes are the feedback diodes. Feedback diodes. We know that here I am using S1, S2 is the main switches means any semiconductor device is used as a switch. I told already. Which devices are used as a switches in voltage source inverter? The devices which have unipolarity and bidirectional capability. Unipolarity and bidirectional capability, that devices are used as a switches. Then these switches we can select. These switches we can select based on the application. Based on the application only we can select the switches. That means these main switches means it may be SCR or it may be a GTO or it may be a MOSFET or it may be a BJT or it may be IGBT, or these are used as a switches. Once we are using MOSFET and BJT and IGBT means this with anti-parallel diodes we can use. With anti-parallel diodes. With anti-parallel diodes these are implemented. But once we are using SCR and GTO means here also we can use anti-parallel diode. Those diodes are nothing but a feedback diodes. But simply you remember which switches are selected in voltage source inverter means which are the main switches having bidirectional capability, bidirectional conduction and unipolarity. And unipolarity. These are used as a switches. Bidirectional and unipolarity. These are used as a switches. Okay? Because it is a which inverter? Voltage source inverter. Okay. Tell. But point to remember, during the operation of this half bridge inverter, don't trigger 2 switches in one leg at a time. Don't trigger 2 switches in one leg at a time. If you trigger two switches in one leg at a time, there is a possibility of shoot-through fault, that is short circuit fault through the source. During the operation of this circuit, you take that precaution. Yes, note, this is the precaution during operation of this circuit. Don't turn on two switches in one leg at a time. Don't turn on two switches in one leg at a time. What is the reason? Because if you trigger the two switches in one leg at a time, there exists a short circuit fault through the source. That fault is called shoot-through fault. The another point to remember, one of the main drawback of this half-bridge inverter is it requires 3-wire DC supply. This 1, 2, 3. How many wires we are using? 3 wires. That's why it is one of the drawback of half-bridge inverter. That is, it requires. So many other drawbacks also there. Later on we will see. Up to now you remember it requires 3-wire DC supply. Okay. Now tell me. One operation of switch is nothing but one operation of circuit is nothing but one on and one off. You forget about positive off cycle and negative off cycle here. Because input is fixed DC. We don't have any positive off cycle and negative off cycle. Then we can operate this circuit in such a way that we want to convert this DC into AC. Like that we want to operate. Then if you want to convert DC to AC means how we can turn on this S1 and S2, that you concentrate. For simplicity, first I will explain this operation for R load. I will explain the operation for R load. Then for remaining loads, directly how to draw the waveforms, that I will explain. By doing the analysis also we can draw the waveforms, but it is a lengthy procedure. That's the reason why first I will explain for resistive loads, remaining loads, purely inductive load, RL load, RLC load, XL greater than XC, XC greater than XL. In these cases, how to draw the waveforms, that I will explain. That analysis and that waveforms I want to draw the for half-bridge inverter. Okay. Yes. It's okay. First you note down this. This is half-bridge inverter circuit. Here any semiconductor device is used as a switch. Among all these, MOSFET is more favorable for high frequency applications. Then you also use SCR, GTO, BJT and IGBT. These are with anti-parallel diodes. These D1, D2 are the feedback diodes. These two diodes, D1, D2 is the feedback diodes. We know what is the difference between freewheeling diode and feedback diode. That statement I already given in the rectifiers. Why I am telling that this D1, D2 are the feedback diodes? These diodes will supply the current to the load through source. Through source it supplies. Through source it supplies. That's why these are called feedback diodes. The diodes which supplies the current to the load through source, those diodes are called feedback diodes. The diodes which supply the current within the load only. There is no current to source. Within the load only it supplies. Then those diodes are called feedback. That is freewheeling diodes. But these diodes will supply the current to the load through source. That's why these are called feedback diodes. Okay. Freewheeling diode is different and feedback diodes are different. Here these diodes are feedback diodes. Okay. Clear? Now see for R load. I want to explain this circuit for R load operation. Then replace this by R load. Purely resistive load. This R load. We know that purely resistive load means Even though it is a voltage source inverter, no need of feedback diodes. For R load na, no need of feedback diodes. No need of feedback diodes. Okay. Then no need of feedback diodes means remove this feedback diodes. Redraw the circuit. You redraw the circuit. This is the inverter circuit for R load operation. Here one operation is nothing but a one time period of operation that I want to explain. Let on and off is in our hand. Based on the type of waveform you want to generate, we can operate this S1 and S2 switches. But point to remember, it may be half bridge inverter or full bridge inverter, single phase half bridge or full bridge inverter. Based on the switching of main switches, we can generate three types of waveform. One is square waveform, quasi square waveform, PWM waveform. That is a pulse width modulated waveform. But in this session, I am discussing with respect to square waveform only. That means we are operating the switches in such a way that we want to generate which waveform? Square waveform. With respect to that only, I am discussing this concept. Okay. On and off is in our hand. Based on your requirement, we can give the triggering, then it is on. Then we can commutate that, then it can be turned off. Okay. Now see, I want to operate this circuit, we want to convert DC to AC. Let for 0 less than or equal to t, less than or equal to t by 2, means in terms of omega t means 0 less than or equal to omega t less than or equal to pi. During this time, I will turn on S1. But still I am not turn on the S2. Okay. Based on your requirement, we can turn on either S1 or S2. Now what I am doing, for 0 to t by 2, I will turn on S1 only. But don't try to like this, analyze like this. S positive, negative, is it S1 is on or not, S2 on, like that. No doubt at all, every switch is under forward bias condition. Here we don't have any positive half cycle or negative half cycle. Based on your requirement, either on or off the switches. S1 is on. If S1 is on, what is the equivalent? S. Still I am not turn on S2. If S1 is on, apply the KVL for this loop. Yes. Enter at positive terminal, take positive. Enter at negative terminal, take negative. Then what is V0 equal to? Vs by 2. If 0 to t by 2, S1 is on, V0 equal to Vs by 2. This is S2. Then what is the peak inverse voltage? Peak inverse voltage in the sense, maximum voltage across the switch under off state. This is under off state now, minus plus Vs, minus plus Vs. Total is, this is Vs by 2, this is also Vs by 2. Peak inverse voltage equal to Vs. It is a purely resistive load now. Then what is I0 equal to V0 by R? That means if S1 is on for 0 to t by 2, what is the output voltage we are getting? Vs by 2. Next. On and off is in our hand. Based on our requirement, we can turn on or turn off the switches. Let for t by 2 less than or equal to t, less than or equal to t. That means you represent on omega t axis for pi less than or equal to omega t less than or equal to 2 pi. Then what we can do here? We can turn off S1. S1 is off. We can turn off S1. Then I will turn on S2. S2 is on. Then if S1 is off and S2 is on, what is the equivalent? This S2 is on. Now apply the KVL for this loop, you tell me. KVL. Then what you get? Minus V0 minus Vs by 2 equal to 0. Then what is V0 equal to? Minus Vs by 2. Means if S1 is on, plus Vs by 2. If S2 is on, minus Vs by 2. Means load is subjected to unidirectional or bidirectional? Bidirectional. That's why we are converting DC to AC. This I am explaining for which load? R load. We know that for R load, voltage and current waveforms are same. Okay. Now based on this, you draw the waveforms, then you get idea how we are getting the waveforms. Just follow these waveforms, parallelly draw the waveforms. Don't wait. Okay. First you note on this, then I will draw the waveforms. Just quick. If S1 is on, plus Vs by 2. If S2 is on, minus Vs by 2. Draw the waveform. First, sorry. Note this one, then I will draw the waveforms. This I am drawing for R load. You know that for purely resistive load, voltage and current waveforms are same. V0 and I0 is same for purely resistive load. For 0 to T by 2, what is the voltage? Plus Vs by 2. This is plus Vs by 2. Then for T by 2 to T, what is the voltage? S minus Vs by 2. Again cycle is repeated. Yes, like this we can get the wave shapes. This is minus Vs by 2. Here S1 is conducting, here S2 is conducting, here S1 is conducting. This is R load now. I told so many times, for purely resistive load, voltage and current waveforms are same. Therefore, for R load, V0 and I0 waveforms are same. Waveforms are same. That is, which waveform we are generating here? Square. I told already. We can operate in three modes, either square wave or quasi-square wave or PWM mode. Here I am explaining the concept in such a way that we are generating which waveforms? Square waveform. This I am explaining this concept in such a way that we are generating the square waveform. Okay, that is for R load V0 and I0 waveforms are same, that is square waveform. That is square waveform. This point you remember? We know that in voltage source inverter, whatever the voltage, whatever the load, you connect any load here, which waveform remains constant? V0 waveform is remains same. Then which waveform will be changing? In the differences, that point I discussed. In voltage source inverter, output voltage, waveform and amplitude independent of load parameters, but output current depends on load parameters. That means for different types of loads, we want to draw the waveforms means, then which waveforms you want to draw? Current waveforms you want to draw. Because for voltage source inverter, output voltage independent of load parameters. Output, once we are generating square waveform means, now it is fixed. Now it is a, whatever the load you can connect, then it is a square waveform only. Based on your requirement, we are generating one waveform. That voltage waveform remains same for any load. Okay, that is output waveform, output voltage waveform, output voltage waveform. Independent of load parameters. Okay, independent of load. Output voltage waveform, you know. But current waveform, yes, but current waveform depends on load parameters. Depends on load. Now for different loads, we want to draw the waveforms. Then which waveform we want to draw? Yes, current waveform. Now see, for different loads, how to draw the current wave. But if it is R load, voltage and current waveforms are same. That this is purely inductive load. Yes, this we are drawing the waveforms. Then you draw the waveform for RL load. This RL load. Yes, now you draw the waveform for RLC, XL greater than XC. XL greater than XC means this is over damped case. This RLC, XC greater than XL, this is under damped. If XC greater than XL means under damped. Okay. Now we'll see the different waveforms for RL, for different loads. Here for different loads, which waveforms we are drawing? Current waveforms. This is I0, this also I0, this also I0, this also I0. We know that even though it is a voltage source inverter, for R load we are not using any feedback diodes. Except R load, for remaining loads, it requires feedback diodes. Except R load. For remaining loads, feedback diodes are used. Now see, for different types of loads, how to draw the waveforms. Mainly concentrate on current waveform. This is voltage waveform. This voltage and current waveforms are same for which load? R load. Like this we are converting DC to AC. Here I am generating the square. We also generate quasi-square waveform, no doubt at all. That is based on switching operation. Okay. Now see, for different types of loads, for L load what is the current waveform? For RL load what is the current waveform? For RLC load XL greater than XC what is the current waveform? For RLC load XC greater than XL what is the current waveform? That you will see. First, yes, we know that except R load, for remaining loads it requires feedback diodes. That this is D1, this is D2. For example, for L load you want to draw the waveform for purely inductive load. One way to draw the waveform for purely inductive load means except R load, for remaining loads it requires feedback diodes. Okay. One way to draw the current waveform is connect inductor here, apply KVL, apply inverse Laplace transform and apply inverse Laplace transform. Based on that you draw the waveform. That is one procedure. If you want to draw the current waveform for RL load means connect RL load, apply KVL, apply Laplace transform and apply inverse Laplace transform. Based on that you draw the waveform. But it is a lengthy procedure. Yes? Here approximately we are drawing the waveform. Based on the approximation of concept we are drawing the waveforms approximately. Now I want to draw the waveform for purely inductive load. For example, here I am connecting pure inductor. Then what is the current waveform through pure inductor that I want to draw? Okay. You know that purely inductive load means VL equal to L into di by dt. No? That means the rate of change of current through pure inductor in such a way that it must satisfy the load voltage waveform. That means for purely inductive load, if any device is conducting means that device must satisfy voltage waveform condition. Whatever the load connector, this waveform will not be affected. This waveform remains same. That means the device which is supplying the current to the load, it satisfies this voltage waveform condition. Tell me. 0 to T by 2. This is 0 to T by 2. 0 to T by 2. V0 is positive or negative? Positive. That means for 0 to T by 2, for 0 to T by 2, we want to get VL is positive. VL is positive means always inductance is positive. Always inductance is positive means di by dt must be positive to make VL is positive. Why VL is positive? Because this is constant. This Vs by 2 is positive. Output voltage. Okay. Di by dt positive. Di by dt positive means rising slope or falling slope? Rising slope. But you know that what is the output we are getting? AC. We are drawing pure inductor now. In pure inductor, current lags the voltage by angle of 90 degrees. Now by satisfying that, now you draw this current waveform. That means for pure inductor, current lags the voltage by angle of 90 degrees. By angle of 90 degrees means T by 4 here. Then to get V0 is positive, then di by dt must be rising slope. This is di by dt. Di by dt must be rising slope. Next. During the conduction of the devices, di by dt voltage must be negative. Here voltage across the load is negative means if T by 2 to T. VL we are getting negative voltage. VL is negative means di by dt must be negative because inductor is always positive. Di by dt is negative means rising slope or falling slope. Right, that is falling slope. Again current lags the voltage by angle of 90 degrees. Again rising. Okay. Again falling. This is for purely inductive load. That's why for purely inductive load, in a voltage source inverter, the current waveform is triangular waveform. Okay. The current waveform is triangular wave. This is for purely inductive load. The current waveform is triangular waveform. Approximately we are trying. Now I want to draw for RL load. Then if you connect RL load means again same procedure. Apply KVL, apply Laplace transform and apply inverse Laplace transform. But it is a lengthy procedure, na? Understood? That's why approximately I am drawing the waveform. RL load means it is pure inductor, we are getting triangular. RL load means exactly we don't get triangular. RL load means lagging current, na? Then current lags by some angle. Now by considering that approximately I am drawing. This we get. Approximately we are trying. Clear? We don't get exactly sinusoidal. We don't get exactly triangular. Okay. Then we get the wave shape like this. It is not exactly triangle. Yes, sorry. Draw this waveform clearly. This is for RL load. This we are getting wave shape like this. Okay. Now RLC XC greater than XL greater than XC, RLC XC greater than XL. RLC means nearly you can get sinusoidal oscillations. Okay. But XL greater than that, you know. RLC circuit excited with AC supply means nearly you can get sinusoidal oscillations. Okay. But XL greater than XC means lagging. XC greater than XL means leading. Lagging. That nearly you can get XL greater than XC means lagging, but it is a sinusoidal oscillation. XC greater than XL means leading. Like this you can get. Here we are not drawing exact waveforms. Approximately we are drawing this. But it is a sinusoidal. Because of RLC, it is a sinusoidal oscillation. Like this we are getting. These are the current waveforms in different loads. But now the question is, how this voltage waveform we are getting based on this that I explained. But now the question is, during the conduction for any load, to satisfy these waveforms, then which device will conduct? In one cycle means in one time period. To satisfy this waveform, here which device are conducting, here which device are conducting. For different loads, to satisfy these waveforms, then the sequence of conduction of devices is important. Okay. Here I am assuming that this positive voltage, this is negative current. This positive voltage, positive current. Negative voltage, positive current. Negative voltage, negative current. Positive voltage, negative current. This lagging and leading currents are taken as a negative currents. Okay. Now the question is, to satisfy this, then which devices will conduct in the circuit? That is important. That you will see the analysis here. Say, for example, D1 is conducting. Let us assume that D1 is conducting. Remaining all the devices are off state. During the conduction of device D1, remaining all the devices are off state. Let this is the assumed current direction and this is assumed load polarity. But so the doubt, yes sir, how the D1 will conduct, positive is connected here and diode is reverse bias, how to say that D1 is, that doubts you can get. But don't think like this. Here diode is conducting means because of energy stored in the inductor. Later on, after discussing what is the sequence of devices, I will discuss how this diode comes into the existence, how the switches comes into the existence. Okay, all these concepts later on I will give. But here I am explaining what is the sequence of conduction of devices to satisfy these waveforms. For example, tell me, if D1 is conducting, this is the direction of current supplied by D1. Same direction or opposite direction? Opposite direction. That is I0 is negative. If D1 is conducting means this positive polarity is connected here, this negative polarity is connected here. This is negative positive and this is also negative positive. Then what about V0? Positive. This D1 is conducting, the voltage applied polarity and assumed polarity both are same, that's why V0 positive. That means if current is negative, voltage is positive, which device will conduct? D1 is. No other device will satisfy this polarity. I0 negative, V0 positive. That means wherever the I0 is negative, V0 is positive is there. In that case, which device is conducting to satisfy that current? D1 is conducting. V0 positive, I0 negative. D1 is conducting. V0 positive, I0 negative. D1 conducts. V0 positive, I0 negative. D1 is conducting. Next, V0 positive, I0 negative. Here which device is conducting? D1. Okay. For example, let us assume that S1 is conducting and remaining all the devices are off state. This is a representation of S1. If S1 is represented in the downward direction means it conducts like this only. Whenever S1 is conducting, listen please, whenever S1 is conducting, the current supplied by the S1 is same that of I0 assumed direction, that's why I0 is positive. If S1 is conducting, then positive is connected here, negative is connected, negative positive, then V0 is also positive. That means I0 positive, V0 positive, which device will conduct? S1. V0 positive, I0 positive, 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 S1 is conducting. Okay, clear? For example, D2 is conducting. Let us assume that remaining two devices are off state. If D2 is conducting, let us assume that remaining all the devices are off state. If D2 is conducting, this is the current supplied by D2. Then what is I0? I0 is positive. Okay. Where this positive plate is connected? This positive plate is connected here now. Where this negative plate is connected? This negative plate is connected here now. This is positive negative, but this is negative positive. Same polarity or opposite polarity? Opposite polarity. Then V0 is negative. I0 positive, V0 negative. Which device will conduct? That is I0 positive, V0 negative. D2 is conducting. Here also D2 is conducting. Here also D2 is conducting. Here D2 is conducting. This one cycle is completed now. One time period is nothing but D2. One cycle means next remaining period. Already D1 is conducting, S1 is conducting, D2 is conducting. Remaining which one? S2. Here which device will conduct? S2. Here which device will conduct? S2. Here which device will conduct? S2. Here which device is conduct? S2. Again cycle is repeated. Then this is D1, S1, D2. D1, S1, D2. This is D1, S1, D2. But here S1, D1, S2. This is the devices will conduct to satisfy these waveforms. The sequence of conduction of devices concept is important. Note down this quick. This I am explaining by analyzing this one. But like this, no need to by heart. Just you remember that sequence I will tell how to remember also. That you follow. Then you can answer any question. Write down as a note. Tell me. What is the sequence of conduction of devices? Simply remember like this. For all lagging loads, first to diode, next switch. For all leading power factor load, first to switch, next to diode. Like that you remember. That is the sequence you follow. That means for lagging power factor loads, the sequence of conduction of devices is is D1, S1, D2, S2. That is first to diode, next to switch. For all leading power factor loads, what is the sequence of conduction of devices? This one. First to switch, next to diode. S1, D1, S2, D2. This sequence you remember. Lagging loads means first to diode, next switch. Leading loads means first switch, next to diodes. These 2 points you remember. Okay. Another point. Voltage waveform is which one? Square waveform for any load. For R load, current waveform is square waveform. For R load, current waveform is square waveform. Yes? But I want to write some points with respect to purely inductive load. Tell me. For purely inductive load, we want to list out some points. Tell me. For purely inductive load, these points are important. What is the current waveform? Current is triangular waveform. How much time each device is conducting? Either D1 or S1 or D2 or S2. How much device is conducting for purely inductive load? Very important points. Already framed in GATE exam and IS exam based on this L load. Okay. How much angle each device is conducting? That is D1 is conducting from this point to this point now T by 4. This point to this point is also T by 4. That is each device, it may be switch or diode. Each device is conducting each device is conducting. How much time? Each device conduction time. How much? T by 4. Next. Time taken to reach peak current. Time taken to reach peak current. To reach peak current. How much time is taken to reach peak current? Tell me. Yes. How much time is taken to reach peak current? I am not asking about peak to peak current. Peak current in the sense from this point to 0. Reference is 0. 0 to this point. Peak to peak means you take minus to plus. Peak means 0 to positive or negative to 0. That is nothing but a peak. That means you take from this one. From this point to peak value, how much time it is taken? T by 4. Time taken to reach peak current is T by 4. Next, we know that for purely inductive load, VL equal to L into di by dt. Na? That is L into di is nothing but a change of current. If the current is changing from 0 to peak value, means IP minus 0. How much time it is taken? T by 4 time. We know this VL equal, because it is a purely inductive, VL equal to L into di by dt. VL equal to L into di by dt means change of current. If the current is changing from 0 to peak value, that means final value minus initial. How much time? dt, how much time it is taken? T by 4 time. Then from this, you can write peak value of current equal to VL into T by 4 by L. Very important formula. Based on this formula also question is framed. Okay, this about what exactly single phase half bridge inverter. But what the main drawback of half bridge inverter, you tell me? At a time how much voltage we are using? Vs by 2 plus Vs by 2. Total is Vs we are giving. But how much we are getting? At a time only Vs by 2 we are getting. That's why output voltage is only 50%. That's why efficiency of half bridge is also 50%. Okay, that is the problem with half bridge inverter. In order to overcome this drawbacks, we are implementing the full bridge inverter. The point to remember, here I explain based on half bridge inverter for R load how we are getting the waveforms that I explained. For remaining loads directly I drawn the waveforms based on the concept that I explained. Okay, then I explain to satisfy these waveforms what the sequence of devices are conducting. Okay, but this is the sequence you follow. For all lagging loads, first to diode, next switch. For leading load, first to switch, next to diode. Okay, this and then for purely resistive load, voltage and current waveforms are same. Because it is a voltage source inverter na. In voltage source inverter, whatever the load you can connect, which waveform is constant? Voltage waveform. This is fixed. Once we are generating square waveform, that is fixed. We can also generate quasi, we also generate PWM, but our analysis is mainly on the square waveform. Okay. Then which waveform will be changes based on the load? Then current waveforms are changing. For R load, what is the current waveform? It's same that of voltage waveform only. For any load, what is the voltage waveform? Square waveform. For purely inductive load, what is the current waveform? Triangular. Then for purely inductive load only, we can know exact how much time it is conducting. That's why I am list out some points here. Okay. For purely inductive load, what is the peak value of current? VL into T by 4 by L. Understood? Okay. This about what exactly single phase half bridge inverter. This you know down. In the next session I will continue with some other points with the half bridge inverter. Then continue with full bridge inverter also. Okay. Then how this drawbacks is overcome in full bridge inverter, that you will see. Okay. In the next session that I will continue. Okay. Clear? Understand? Note down these points.